Hey everyone, it's Mr. Canfield. Today in BC Calculus, we're going to do what's called Euler's method. And this is essentially a way that we're going to be able to graph solution curves. That's kind of the long, or the short version of what's going to happen. So if you remember back when we did slope fields, we would have like a slope field like this, and we would start at a point, and we would kind of follow the trend of the slope field from an initial condition. And Euler's method just puts a little bit more rigor to it. The good news is Euler's method is very easy, actually very easy. Oh, I'm totally glossing over something. The dude's name is Euler. I know. It looks like Euler. It's not. It's Euler. He was Swiss, okay? So the Swiss have different ways of pronouncing things. So just understand, when people talk about Euler, they're not talking about like a hockey team. They're talking about the man whose name looks like Euler. So here, this little picture kind of helps us see what's happening. So basically, if we know a differential equation and we know its starting point, we can use little tiny slopes and create approximate curves. So consider the differential equation dy dx is equal to x plus y. All right. And we know the initial condition f of 0 is equal to 3. So here's the deal. This is dy dx, right? This is y prime is equal to x plus y. There is some unknown initial equation that we could say like y is equal to blah, 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 but there's no derivatives in it. Instead of finding that, we're just going to find a single solution curve since we know f of 0 is 3. So we want to find out, we're going to approximate what f of 2 is. What is f of 2? And it tells us how many steps to use. If it didn't tell us how many steps, it's really up to us what we do here. But if you remember, this is kind of similar to linear approximation. Back when we did linear approximation, we knew, well, hey, if we know the y value at a certain x value, well, we could find the slope, right? Like if I go in, I know that we have the point 0, 3. Well, I could go in and I could plug in 0, 3 here and find out, well, the slope there is 3. And if I just kind of extend that slope a little bit, I'll eventually get to the x value 2 with that slope, and that'll give me some sort of an approximation of the answer. But our slope is this changing beast. So instead of just going start at 0, 3 and just jump straight to 2, let's jump part of the way to 2. So like it says use 4 steps to get to 2. So that means we'll go by halves, right? So 0.5 and then 1. And then 1.5, and then we'll get to 2. And we can just kind of organically get there. So well, what's dy dx? Let me see, I think I need to use my smaller. Is that still, yeah. What's dy dx at 0, 3? We can go plug it in, we get 3, right? Okay, so that means the slope here is 3, but what's my new y value going to be? So the way that we do this, mechanically, like you might have already figured out that it's 4.5, so good for you if you have, but mechanically speaking, well, if I know that dy dx is equal to 3, I actually know what dx is based on this, what we've done here. Dx is, we're going by 0.5, right? The difference in x each time is 0.5. So I actually could say, well, dy is equal to 3 dx, right? Dy is equal to 3 times 0.5, and 3 times 0.5 is 1.5. And so literally, dy, the change in y, is 1.5. So if the change in y is 1.5, well, my original y was 3, right? So that means my new y is going to be 4.5, because it's going to change by 1.5. So we were at 0.3, now we're at 0.5, 4.5. So then we recalibrate and we go, okay, well, what's our slope here? What's our dy dx here? Well, 0.5 plus 4.5, right? We add x plus y, it's 5. And here's the thing, this work is always the same. It's going to be dy dx is equal to a number, and then we're going to multiply that number by dx. The thing is, Euler's method, dx is always the same thing when we do a problem. So you find out your slope, you multiply it by dx to get your new dy. So now I'm at this point, and I know that dy dx is 5 now. So 5 times 0.5 is 2.5. And I add that, because it's my change in y, right? So I add that to my current y. So 4.5 plus 2.5, it's 7. So now I have to find my new slope, right? Well, my new slope is going to be x plus y. So 1 plus 7 is 8. But dx is still 0.5, so 8 times 0.5 is 4. So I add that to my y value and get my new y value of 11. This one's going to be a little bit gross, because our slope now is going to be 1.5 plus 11, so 12.5. So 12.5 times 0.5 is going to be 6.25. And that means that the y value at 2 is going to be 11 plus our dy, 17.25. So f of 2 is approximately 17.25. So I just want to visually show you what we just did. We know dy dx is equal to x plus y. And we know that f of 0 is 3. So what we did, well, that's actually, let's say 3 is down here. So what we did was, we said, okay, well, I'll start going, and then, what's the slope now? Because m was 3 there. What's the slope now? Oh, it's more now, okay. Oh, and then, hey, what's the slope here? Oh, it's more. Hey, what's the slope here? Oh, it's more. And so instead of just using like an initial, like, okay, and just following that slope out, we followed our changing slope to find out what it was going to equal. So all I'm going to do today is a bunch of examples like this, well, whatever the notes does, and we'll go from there. So if this first example made sense, Euler's method makes sense to you. If it didn't make sense, try to pick it up in the next example. Okay, so next example time. What color should I use? Should I use this one, this one, this one, or this one? Good choice, we'll go with this one. All right, dy dx So this one says dy dx is x plus 4 over y, and f of 0 is equal to 4. And it says, hey, what's f of 1? Right? So all we have to do is use Euler's method. So I don't do Euler's method without the table. And I do like to just kind of have all of my pieces in a row. Everyone does it a little bit differently. My 4 and my y look way too similar. I got confused. So my initial xy was 0, 4. And if I'm trying to get to 1, well then I know, and it said to do 4 equal steps, so 0.25, I'm going by 0.25s then. So, let's see, x plus 4 divided by y. Oh, so that's 0 plus 4 over 4, so it's 1. And dx is 0.25. So that means that dy is, and so we always take, we take our dy dx, we take our slope times dx to find out what dy is. So it's 0.25. So my change in y is 0.25. So that makes my new y 4.25. All right. So, oh, this is going to be awful, isn't it? Let's see. I'm going to do x. So top is 4.25, bottom is 4.25. Oh, it's still 1. That's pretty sweet. Oh yeah, and our dx is 0.25 each time because that's how much I've added in my x's. So let me see if I can do a better job explaining what I'm doing here. If you get what I'm doing, you just do the process, get it. We know that our x value, we started at 0, we're ending up at 1, and we're supposed to take 4 equal steps because the problem asks to do 4 equal steps. So I know in my x's, I'm going by 0.25 each time. That's called our dx. We're also able to calculate what dy dx is because we have that. And so what I can do then is I can calculate y values along the way and reevaluate from each of those y values. Well, how much am I going to go up between these two y values? Then how much am I going to go up between these two y values? Between these two y values, then between these two y values. And we're going to end up at a new y value that's close to the real y value of the actual answer. This is going to get us close to the actual answer. So let's see, 1 times 0.25 is 0.25. Add it on here, I get 4.5. And then x plus 4 over y. Wait, 4.5 over 4.5, it's 1 again. So I just add 0.25 again, I get 4.75. It's 1 again. So I get 5. So I got that f of 1 is approximately equal to 5. The way that worked, I kind of feel like it's going to be exactly 5. And there is a way to actually do this, to do these problems, to find out like what y actually equals and find the function and then plug in 1 to that function and see if it actually is 5. But this is a way to not need to do that. Okay. too much further, yes, this is always on the AP exam. Let's see. Number 3 says, let T of T, well, that's not confusing, denote the room temperature in Fahrenheit of a cup of coffee at time T in minutes. Room temperature is 70 degrees and the coffee is 190 when it first comes out of the microwave. Old me would scoff at somebody microwaving coffee, but I do it all the time now. I just don't care anymore. The coffee's temperature is described by the differential equation d big T d little t equals negative 0.1 times big T minus 70. Complete the table using Euler's method for 10 minutes, plot your result on the accompanying slope field, then solve the differential equation to find the actual temperature. Okay, so we're gonna fake solve it, then we're gonna use Euler's method to get an approximate, and then we're gonna really solve this to find out what the actual pure answer is. So for me, doing this by hand sounds annoying. So I am more of an Excel person, or like I would use Google Sheets to do this, but I'm on my calculator right now. Oh wait, big T. Big T is actually Y here, and I'm not able to do that here. So also notice he leaves out like the spot for dt here. Also, I think he meant to write dt. So let's see. Zero and 190. I mean, I guess I could still, yeah. I just have to remember that whatever I graph here isn't going to be what actually works for the real thing, because that's more of a y value, but I'm going to go into my table. Right, because now we can get a whole bunch of different, oh wait, silly me, I'm underthinking this. So we're actually plugging in 190 to start, right? So 190 is going to be like my input here, and my output is going to be the slope. Because it says dt, our slope is the y, and this is over on that side. So if I go to independent ask, then I can do this. I can say input 190, you get negative 12. So what's my dt here from our first to our second? It's 1, right? So we actually just go down 12. So I get this to 178. So then what is it at 178? Negative 10.8. And if you think about the problem, this should make sense. And especially if you understand heating and cooling and how temperature tends to approach equilibrium in like in an environment. Like if you bring a hot thing into, it's going to approach the ambient temperature. So 178 minus 10.8. I don't know if you knew about this, but you actually can just do that if you want to be lazy, and it'll do it for you. 167.2. So I got negative 9.72. If you want to fast forward, you can. I'm not going to edit this out. I'm just going to go through and finish it. So it's super tedious, right? Oh, 0.875. Oh, I ran out of space. $148.75. 140.875. 133.7875. Oh, wait. So this is definitely begging to be a computer program. 133.7875. Okay. So another way to do this, if I don't want to do it that way, I could say negative. Oh wait, I've got this in y1, right? So I could say 133.7875 minus 6.37875. I can click store x, right? And then I can go and have y1 pop out. And then I can just do take that and add that onto it. And that's my next one. And then take that and store that as x. Oops. Plug that into y1. Take that and add that onto it. So let's see. I got, oops, went a little far. 127. So 127. 121. 116. Okay, so I have one more to go. So I'll take this, plug that into my $111. All right. So my approximate time, or my approximate temperature at 10, what is that, 10 minutes, is 111.8509788 degrees Fahrenheit. So what we're going to do now is we're going to look at how to do this exactly. So what I can do is dt is equal to negative 0.1 t minus 70. Okay, we're going to solve this differential equation. So what this means is we're going to integrate this. The way we integrate is we make sure that the variables are on the right side. So if this was a little t, then we could just integrate it as it is. And maybe it would be helpful for me to say dy dx, right? That makes this y. If this had been dy dx and this had been an x, we just take the integral and we have our original function with a plus c on the end. But unfortunately, we have this. What I can do, though, is I can multiply both sides by dx, and I'm going to keep it as dx just to kind of help you see what's going on. If I divide both sides by y minus 70, well, check it out. I get dy over y minus 70 is equal to negative 0.1 dx. Believe it or not, these are very easy integrals. The right-hand side is just negative 0.1 x, and the left-hand side, well, this is 1 over that stuff, right? So I could just say that it's natural log. Excuse me. Because the derivative of this is just 1 over y minus 70. And here's the thing. We know, well, this was like x and this was like y. We know when x was 0, y was 190. So what happens when I plug in 0 here and 190 here? I get ln of 190 minus 70, 120, and then I get c. Oh, c is equal to ln of 120. And you know what? No, let's do this a different way. Instead of doing that, what you'll usually do for these is you'll solve for y first. So there's a way that we solve this for y. It's pretty easy. Like, they always kind of work out the same. I'm going to try to do it slowly so that I make sense out of it. We want to get y by itself, so I got to get rid of this ln. And the way that we'll get rid of an ln is we're going to e it. But you can't just e one thing. You got to e the other side too. So when you do that, and let's talk real quick. Let's assume that y is always going to be 70 or more. So here's the thing. For a question like this, we're talking about a cup of coffee in a room. The room is probably 70 degrees. That's probably where it comes from in the formula. So we can assume that, like, if you take a cup of water and you put it in a room, that cup of water is never going to get colder than the air around it, unless it starts out colder than the air around it. Like, if it starts out colder, it's going to warm up. If it starts out warmer, it's going to cool down. But it's always going to hit that, like, it's always going to aim for that room temperature. So I don't actually need these absolute value bars for this question. So I can say y minus 70, right, because we just canceled it out with the e-ing it, is equal to e to the negative 0.1 x plus c. So we're going to do a little magic trick here that you can always do. So this next step, I'm only going to write this when I'm teaching you how to do it. You never need to write this next step. I'm just going to remind you real quick. What's 2 to the 3 times 2 to the 8? It's 2 to the 11th, right? Because you add the exponents together. So what's 2 to the 4th? Could I say it's 2 to the 1 times 2 to the 3? I could break it down right like that, right? What I'm going to do here is, I see this is e to a sum. I could say this is e to the negative 0.1x times e to the c, right? So what we do, wait, e to the c, this is just equal to a number, so it's a new c now. Excuse me. It's different to that c that I was calculating earlier. So now I can say y minus 70 is equal to c e to the negative 0.1 x. And so I can say y is equal to c e to the negative 0.1 x plus 70. We'll do a lot of these this year, so hopefully it'll start to make sense for you if that didn't quite work out. And we know some things, right? We know that when x is 0, y is 190. So when x is 0, y is 190. And this actually is pretty easy, right? Because negative 0.1 times 0 is just 0, and e to the 0 is just 1. Subtract the 70 from both sides, you get 120. So c is 120. So really close to the thing I got earlier. I got ln 120, now it's just regular 120, because it's a different c. It's a slightly different context. So I can say y is equal to 120 e to the negative 0.1 x plus 70. And I guess I should get away from this xy language because we had big T and then little t there. Totally different. But what I can do now is I can say, okay, well, earlier when I was approximating using Euler's method, I got 111.85 mess. Given the pure answer to this, what happens at 10 seconds? Oh, so we're off by about 3 degrees. That's not bad. Can you feel the difference of 3 degrees? Like, I struggle with that. So in reality, the coffee is going to be about 114 degrees, which is still hot, but it's not as scalding hot as it was when it started. So you can also go in and go, 0, 190, 178. I mean, if you really feel like it, if you want to, you can go plot the points. I don't really want to. But it's going to be like, it's going to be something like this. And so it seems like the real thing's going to be like, ending just a little bit different. So anyway, let's keep going. To determine the approximate location of the relative minimum for the functions whose differential equation is given by Euler's method with a step of 0.25 is used. If the initial value, so by the way, this kind of like melted my brain a little bit, too many words, but I'm just going to keep on going and see if I can't get back there. Euler's method with a step of 0.25 is used. Cool, so I already know that if I use Euler's method, I'm going to use my table. You can always use an abbreviated table. You don't have to use all the pieces I use. But I like using the longer table because it's really spelled out for me. My step is 0.25, so I know dx is 0.25. So I'll be multiplying by 0.25 at some point. If the initial value is 0.4, 0.4, plug it in there, times 0.25, you get your dy. What interval does the relative minimum for f of x lie? Oh, relative minimum. Well, a relative minimum is going to happen here, right? That sort of thing. When f prime is negative, hits 0, and then f prime is positive. So we're going to want to look and see. Let's see. We're going to want to look and see, okay, when does dy dx change from negative to positive? That's how we'll know. So 2x minus y plus 2. Okay. So 2x minus y plus 2. Well, that's going to be 0 minus 4 plus 2 is negative 2 times 0.25. That's negative 0.5. So I don't know the answer to this. I don't remember it. So I just went to 2 arbitrarily. I was like, yeah, I'll go to 2. So that's going to give me 3.5 here. 2 times x is, you know what? Hold on. 2 times x. All right, guys, let me be honest. Here's how I would really do this. All right, sorry for the shaky cam. I gotta show you, this is what I really do. Because this is preposterous. No, not slides, silly. I'm gonna go to Google Sheets. And what I'm gonna do is I'm gonna make formulas. I'm just doing this by hand, it's silly. Let's see. I'm gonna make x, y, dy, dx, dx, and dy. Okay, so 0.25, or no, it started at 0. You know what, I'm gonna continue to screen grabbing it. Okay, so I'm just copying what I had from the table, right? So it was 0, 4. So dy dx, what I'm going to do is I'm going to type equals, and I'm going to type 2. So 2x would be 2 times this guy, right? So I do 2 parentheses, click, close it. So it's going to do 2 times that guy minus that guy plus 2. Cool, what did I do wrong? 2 equals 2 times that. Wait, why is this giving me a problem? Oh, it's because I didn't say times. So I had to click 2 and then use the asterisk for times. All right, so cool. So I got that. So here's my x, here's my y. My dx is 0.25, and this is equal to that times that, right? So negative 0.5. So here's the cool thing. Well, here, this is 0.25, and then this is 0.5. So I can select those and drag that little box, and it'll continue the pattern as far as I want to go. And then here, I can say that this is equals this plus this guy. I get 3.5. And then I can drag this down, and it now continues that formula, but for this one. And then continue these all down because it's 0.25 all the way down. And then this one, it takes this times this, it gets me that. So to get my next cell here, you just drag it down and it gets it. So what I could do, if I drag all these down, it'll do them all for me. And I could keep going. But the important part to this question was, it was asking where a relative minimum could occur, and a relative minimum can occur. A relative minimum can occur when our slope changes from negative to positive. So that's, I'm looking at dy dx. I see negative slope, negative slope, negative slope, positive slope. So that means that somewhere between 0.5 and 0.75, we have a negative slope changing to a positive slope. That means there's a zero slope somewhere in here. So we have a we have a relative minimum somewhere on this interval. All right, well, I hope that little diversion was helpful. You don't need to know how to do that. If you just kind of know how to crunch numbers, you'll be fine. Consider the following differential equation. Dy dx is equal to e to the 1 minus y. Initial condition f of 0 equals 1. Find the difference between the exact value of f of 1 and the Euler approximation of f of 1 using two equal steps. Ooh, this is a good AP question. So, let's see. F of 1. So we got 0, 1. And so here's x, here's y, right? 0.5, 1. So dy dx. This would be a non-calculator question, would be my guess. So dy dx here is going to be, let's see, that's e to the 0, so it's just 1. And then dx is just 0.5. So that means that 1 times 0.5, it's 0.5, so this is 1.5. So that means our new e to the 1/2 is going to be e to the 1 minus 1.5. What? So that's going to be e to the negative 0.5. Never mind. I think this will be a calculator question. So e to the negative 0.5 times 0.5 plus 1.5. So our new value is 1.803. So our approximation is 1.803. Let's calculate the exact one. So we're going to have to separate the variables again. So we'll multiply the dx over here, and we'll divide by this one over here. All right. So I see a trick that I'm going to want to do here to make my life easier, because this integral looks really bad. The right-hand side looks wonderful, though, right? Whew. Challenge. Because it's just 1, right? The left-hand side, though, instead of saying 1 over e to the 1 minus y, I'm going to say that this is e to the negative 1 minus y dy. I'm going to distribute that negative now. And I'm going to say this is the integral of e to the y minus 1 dy. Now I've got a pretty nice integral over here. So e to the y minus 1 is equal to x plus c. So I want to find out what's y when x is 1. But I need to... Okay, so I'm actually going to... I'll keep solving this then. So it's worth our time to do a little bit of heavy algebra. Or pre-calculus. So I'll ln both sides. So notice how when it was ln, we e'd both sides. Now that it's e, we ln both sides. Cancels out, we get y minus 1 is equal to ln of x plus c. This I don't have a fun little trick to do, so it's going to be stuck. So I got y is equal to ln of x plus c plus 1, and what's our initial condition? 0, 1. So when x is 0, y is 1. So ln of c plus 1 is equal to 1. That means this has to turn into 0, so c is 1. So we can say y is equal to ln of x plus 1 plus 1. So then, if I want to know what happens when you actually plug in 1, you get y is equal to ln of 2 plus 1. So that's our actual answer. 1.803 is our approximate answer that we got a minute ago. So all I've got to do is take ln of 2 plus 1 minus 1.803, and that's going to give us the difference of, did I ask for, which way did I ask? Find the difference between the exact value and the approximation. So that would be exact minus approximation. So I got negative 0.10985. Okay, so a lot to take in here. But so like this, we could look at this as like the error, right? That's how far off our approximation was. So if this was money that we were talking about, you're 10 cents off of the real thing using this approximation. I know I kind of threw a lot at you. This is meant to be just kind of covering everything. Please let me know how I can help, though. I'm not trying to leave anybody out to dry with this. All right. Bye.